So today our first speaker is Alba Cervera-Lierta, who will be telling us about the quest for the final quantum computer. So Alba did her doctoral studies in entanglement applications in quantum information at the University of Barcelona. She also worked on quantum algorithms for near-term applications at the Barcelona Supercomputing Center. Her background includes particle physics phenomenology, multipartite entanglement, and quantum information. She's currently a postdoctoral fellow at the Alain Asperger Group at the University of Toronto, where she's working on variational quantum algorithms and computational tools for quantum simulation. With that, I'll hand things over to Alba and pop out. We've got 1 minute left.
Take it away, Alba. I will wait 1 minute at least. Let me share my screen in the meantime. Okay, I will assume that we lost Paul again. But yeah, I see that people can see my screen, so I will just start if that's okay for you. So let me start. I will try to give this talk with a very basic knowledge in quantum computing, so I don't expect that any expert in this room. So my idea is that you will have a general overview of what's going on in quantum computing, what are the most important features of it, what is the state of the art of this field, etc. So the outlook of my talk will be very simple. Like I will answer the questions that what is a quantum computer, why we need a quantum computer, how it works, where are being constructed, who is constructing these devices, and when we'll have a quantum advantage experiment, that is an experiment that cannot be simulated with a classical computer efficiently. So let me start with a brief story of quantum mechanics for those that are not familiar with this field. So quantum mechanics is the field in physics that study the phenomena at the microscopic phenomena or high energy physics phenomena. And it started at the beginning of the 20th century to solve some thermodynamic problems related with the black body experiment, etc., to solve some inconveniences that appears in some experiment. But it was not until the 1926 that we have the postulates of quantum mechanics, which were the mathematical formalism needed to understand this theory. Later on, we have the infancy and what I call infancy and childhood of quantum mechanics, where we started to learn and control the quantum mechanical world, and the first applications started to appear. So for instance, we have transistors, solar cells, GPS, laser, magnetic resonances, etc. And some people call this phase the first quantum revolution because we started to have the first applications of it. Later on, I decided to call this adolescence, the 80s until 2000s or so, because we started to study with much more detail the field of quantum information, and we discovered that we can use quantum phenomena for communication and for computing. So from these years are the most famous algorithms in quantum computing, like the factorization algorithm, the Shor algorithm. We have the first experimental implementations of quantum computing, quantum logic gates like the CNOT gates, and also the first big experiments of quantum simulation with Bose-Einstein condensates. And finally, I consider that now we are in the jaws of this theory, which is the quantum 2.0, let's say. So it's the second quantum revolution. We now have the first quantum chips, the first quantum teleportation satellites and quantum communication satellites, and very recently, the first quantum advantage, quantum supremacy experiment. So the first proof that we can do things with a quantum computer that are not possible with a classical computer. So this is the second quantum revolution called by many people, and this is the big framework of this second revolution. The theoretical framework is, of course, quantum mechanics. And on top of that, we mixed that with information theory. And it appears the quantum information field, which is super extensive. But in particular, it has three big applications. The first one is quantum communication, which includes quantum cryptography, how to communicate using quantum phenomena. The second one, the one that I will focus my talk, is quantum computing, which I include quantum simulation inside of it. And the third one is quantum sensing, which includes quantum metrology, so how to construct sensors that are super precise, etc. Okay, so what is a quantum computer? I will try to define it in a more simple terms. To me, it's a device capable of processing data in a quantum mechanical form, or in other words, a device that uses the properties of quantum mechanics to process data. Something important to keep in mind is a quantum computer is not only quantum. The quantum part of it is the hardware, so where the operations are performed, where the data is processed. That's why it's quantum, because if data is quantum, we need something quantum to process it. But it also have a classical part, which is the software that controls this quantum hardware. So you can imagine it as we have some laptop in our lab, and we send a set of instructions into our quantum hardware that will consist of microwave pulses, laser pulses, etc. And the hardware will implement whatever algorithm that we decide. And then the hardware returns the result, which is a classical bit string that we post-process later on. So in the end, we have a classical computer that controls what happens in a quantum device. And inside of this quantum device, we have the qubits, which are the minimal units of quantum information. So I wanted to make clear that we still have classical computation in quantum computing. So maybe I should start with this question: why we need a quantum computer in the first place? So there are many reasons for that. I will start with the historical reasons that why we wanted to have this device. So for instance, we have these physical models, which in this case are molecules. And molecules, chemistry in general, everything, it's described by quantum. So each time that we want to simulate, we want to understand a chemistry molecule, etc., we need to do quantum mechanics here. So if we want to simulate that, we need to introduce and codify all the quantum phenomena into our classical, into our computer that is classical. If we want to do more sophisticated things, like, for instance, study protein folding or study new drugs, etc., all the simulations, etc., are performed classically with supercomputers, with our laptop, etc. But still, the phenomena that we are trying to describe is quantum. If we want to study new materials, superconductivity, etc., this phenomena is also quantum. And besides all these things related with quantum simulation, in the end, we also know that there are some problems that cannot be solved efficiently with a classical computer. But we have found some complexity classes, in particular the BQP class, which is one of the most famous ones, that are those problems that can be solved efficiently with a quantum computer. So not only we have quantum simulation experiments, but we also know that there are some mathematical problems and some very hard problems that can be simulated efficiently with a quantum computer. So in the end, for doing all these things, in the last years, we always have a computer, of course, which is not quantum. We also have supercomputers that can be super powerful, but still not quantum. So why not constructing a device that is quantum, so it shares the same properties as the things that we want to simulate, as the things that we want to study? So we don't have all this overhead that comes from simulating quantum mechanics in a classical computer, which is exponentially hard for the reasons that I will show you later. So in the end, that was the historical motivation of building these devices, to simulate what happens in nature, because in the end, nature is quantum. All the things that interest us, like chemistry, protein folding, new materials, etc., they are quantum. But not only that, but we also discovered that if we construct these devices, if we compute things in a different way, why not using also these properties to compute other things, for instance, for machine learning, for quantum machine learning? In the end, we are discovering a new way of processing data. So why not using this other way to explore other possibilities beyond quantum simulation? Okay, so how does it work? I have no time to go into details, and that's not the aim of my talk. I just wanted to mention the very, very general concepts behind quantum computing. And the most famous one is the basic information unit. So as you know, classically, we have bits, which are zeros and ones. But with quantum mechanics, we have what is called a qubit, which is superposition between a 0 and 1 state. So a qubit can be in the 0 state, can be in the 1 state, so it includes the bit representation, but it can also be in a superposition of 0 and 1 state. So as you can see, we are processing data in a very different form. We can encode data in a very different form. A property of quantum mechanics is called superposition, and that extends to more than one qubit. So for instance, if we want to codify the state of 2 qubits, we will need 4 bits for that. So we need to we can codify the 0, 0 state, the 0, 1, the 1, 0, and the 1, 1, all in only 2 physical units, which will be 2 qubits. If we want to do that with bits, we will need at least a vector of 4 components. So this extends and to all possible, to more and more parties. So in the end, that's the reason why simulating quantum physics is exponentially hard with a classical computer, because we need an exponentially large vector, and of course, all the operations on it will be matrices that are exponentially big. Another property that arises from quantum superposition is a particular case, which is entanglement. So we can have superposition in a way that we cannot distinguish the 2 different qubits states. When that happens, we call that these 2 qubits doesn't have its counterpart in classical physics. These things have been entanglement has been proved powerful in all these quantum algorithms, and is basically one of the reasons why quantum computer is so powerful in some problems that classical computer isn't. Then from the experimental point of view, we need to find a way to encode these qubits and to have these qubits experimentally. So in the end, a qubit from a physical point of view, it's a system, but that it's quantum, of course, and have 2 well-defined states, as similarly as the bit is constructed using a transistor, which has 2 well-defined states. So we can do that in the most simple representation of it is the atomic orbital. So we have the ground state and the excited state. So depending on where the electron is located with respect to the nucleus, we have different energy levels, and we can codify these energy levels as 2 different states. But not only that, we can also do encode a qubit in a more sophisticated physical device, which, for instance, we have the superconducting circuit. In this case, it's the transmon qubit, which is a circuit that can have different energy levels, and depending on the level, we are in the 0 or in the 1 state, or we can even have more states. And these are one of the most used ways of encoding data. We can also have photons, for instance, and encode the qubits in photonic states. And there are many, many more. But the important thing is we need a quantum system that has 2 well-defined states that we can control with pulses, lasers, etc. So let me move to where are these devices being constructed. And the point in the last, I would say, 5 years or so, there has been like a race between different countries to invest a lot of money, not only in quantum computing, but also in quantum technologies. So we have the European Quantum Flagship, for instance, which invests 1 billion euros in quantum technologies. We have the US National Quantum Initiative, and we also have in Canada, Quantum Canada Initiative, which is also 1 billion Canadian dollars. And in the end, what is trying to do all these countries is to invest a lot of money in all this second quantum revolution, and trying to create this quantum computer, and also to develop new algorithms and new applications that can be used for that. So we are basically in a kind of race to see who will construct the first useful quantum computer. And there are many, many proposals around the globe. So everybody is trying very hard to obtain these devices. From a private sector point of view, we have many companies that are bidding in this race. And we have the well-known companies like Google, IBM, Microsoft, but we also have many, many startups. So in the end, quantum computing and all this field was originated in universities. And once we discovered that we can do that experimentally, that is not only theory, that we can really construct these devices, many people from academia decided to found their own companies and try to pursue this final goal. And that's the origin of many startup companies like Rigetti, Xanadu, Control, etc. So all these companies are founded basically by people that came from universities. So they are developing a quantum computer. They are trying to find applications for that and market applications, but they are also doing research. So that's a very particular way of working at this moment. And it's really exciting because you can basically decide if you want to go to university or you want to go to some private company. And we have all these companies. We have even more than that. So I just wanted to put some of them. But we also have software companies that are trying to find these applications that design new algorithms, etc., but also design all the software necessary to control the quantum computer. And we have many of them. Many of them are startups. And the point is that they are appearing more and more. And from the hardware point of view, all these companies, not all of them bid with the same technology. Some of them will use superconducting circuits that I mentioned before. Others will use photons. Others will use ions to codify the qubits. So the point is not even clear which technology will be the one that will deliver the final quantum computer. So we are still researching in this area. I will also mention what are the quantum initiatives in Canada, and because there are many, so we are very fortunate here. We have the startup incubator, the Creative Destruction Lab, which has we have a section only specialized in quantum technologies. We have software companies like Zapata and OneQubit, and we have also people that are building these devices, as Xanadu, the Wave, or Anion Systems. And on top of that, we have all the research centers and universities, like, of course, University of Toronto, where I belong, but we also have in Waterloo, the Vector Institute in Toronto, University of Victoria, Sherbrooke, etc. All these universities have research groups that are working actively in quantum computing in particular. And in Toronto, of course, we have many of them, almost all of them. So it's a very nice city to work in quantum computing at this moment. Another big question, when will we have this quantum advantage? And the problem with quantum advantage is that first we need to overcome many experimental difficulties. So I believe that it can be quite well summarized with this drawing. So imagine that we are in the classical world when we have classical computers, as you know, supercomputers, etc. And we want to arrive to the fortress of fault tolerance, which is where the final quantum computer lives, basically. To go there, we need to first cross the desert of deadly decoherence. So decoherence is the physical phenomena that breaks all the quantum mechanical properties. So if in the middle of your quantum algorithm you have decoherence, your algorithm will not work. So that's why you first need to overcome this problem, which is hard experimentally, but that's one of the reasons why these experimental challenges are. If we manage to hold the coherence until the end of our quantum algorithm, we arrive to the burden planes of NISQ. NISQ stands for Noisy Intermediate Scale Quantum Computation, which means that, okay, we have coherence, but the quantum gates are not perfect. They are noisy, which means that they are not implemented perfectly, obviously. So here, we can do some things interesting. We can run some algorithms, and I will explain later a particular example. But still, many algorithms that we want to run cannot be run if our computer is noisy. So to finally arrive to this fortress, we need to cross the mode of error correction, which means that we need to error correct all these qubits, noisy, to become logical qubits, which means that they are perfect, they have no errors. And just to make some examples, who lives in this fortress? In this fortress lives the factorization algorithm, the well-known Shor algorithm, Grover-Search algorithm, and other algorithms that basically claim and prove exponential advantage in comparison with classical computation. And in the planes, we have the variational algorithms that I will explain later. So in the end, the important thing is houses in the fortress are made with logical qubits, and houses in the planes are made with noisy qubits. And to obtain a logical qubit, we need at least 1,000 noisy qubits to correct it. That's why this is the huge overhead that quantum error correction has. And that means that at long term, we will need quantum computers of millions of qubits just to have these logical qubits and to be able to run this factorization algorithm, Grover-Search, etc. So, okay, what can we done at, let me just say that we are now in the number one here in the quantum supremacy part of quantum computing, because very recently Google just proved an algorithm that cannot be simulated with a classical computer. But still, we still need to find an application, a real application that uses quantum computing and at the same time cannot be simulated efficiently with a classical computer. So we are now in step one, but moving towards very recently, I believe, in my opinion. So I believe in the next 2 years as much, we will have the first quantum advantage experiment, the real one, the one that implements something useful. So let me check. Okay, I will finish very quickly. We have the NISC algorithm, which are this variational algorithm that mixes quantum computation with classical computation. So I have no time to go over that, so I can explain you later on if you are interested on that, but let me summarize very quickly. We have our algorithm codifying this quantum circuit that depends on a series of parameters. And with this quantum circuit, we compute what is called an expected value of some operator that encodes a molecule, for instance. And with this operator, we just try to minimize a loss function. Sorry? Okay, I'm finishing in a few minutes. So we try to minimize this loss function, but this loss function will suggest new parameters to our model. So finally, we complete this loop, and the important part of this loop is this is a classical part. So variational algorithms mixes quantum computing with classical computation. As I said before, we have many experimental challenges, like which is the best technology, and also if we want to run fault-tolerant algorithms or noise-resistant algorithms. The important point is that we have two different options, and we can still run very interesting algorithms even at short term, even if our quantum computer is not perfect. And let me just mention very briefly that this is not the end of classical computing, because we still need a classical computer to control a quantum computer, and because we don't even need a quantum computer for everything. We need a quantum computer just to solve those problems that cannot be solved efficiently with a classical computer. So in the future, we will have both. We will have quantum computers and we will have classical computers. And finally, and this is my final slide, I just wanted to mention this quantum calling for everybody that is interested in this field. We need people from different backgrounds just to find new applications, to find new algorithms, to understand which are the platforms that we should use, for instance, trapped ions, superconducting circuits, photons, etc. And we also need people to program these devices, to design the programming language that will control the quantum computer. And that's why in the end there is a field that is in expansion and will accept people from many different backgrounds, because we need everybody here. This is my final slide. Thank you very much for your attention, and happy to answer more questions and explain in more detail some things that I said.
That was fantastic. Thank you, Alba. We got a few questions here. The first one was about the best introductory book on quantum computing. So we had a couple suggestions from the chat. Actually, the next speaker, Alejandro, has suggested the classic Nielsen and Huang's book, Quantum Computation and Quantum Information. But I'm curious, what's your pick for the best introductory quantum computing book?
Yeah, for sure, the Nielsen and Huang is like our Bible in quantum computing. So everybody has studied with that book, I would say. Recently, there are many other resources, especially in the ones that are being done for companies. So I will recommend in particular the Kiski textbook, which is developed by IBM. There is a lot of resources there that just present step by step how to construct quantum algorithms and the basics of quantum computation and applications. I will also recommend the Xanadu and the Penny Lane, which is the language of Xanadu, tutorials in quantum machine learning, because there are many of them. They are very well written, and they just explain the quantum machine learning algorithm and how to implement that using their language. I would say there are many other textbooks, like okay, now I cannot think about anyone in particular, but I would say that, yeah, if you look at the resources that some companies are offering, that's a very good tool, because normally these companies also present the code to implement the algorithm. So you can understand the physics, but you can also see how to program a quantum computer. That's what I would recommend.
Awesome, thank you. We've got another question about the error rate that requires many qubits in order to have one logical qubit. How firm is that error rate, and to what extent is it theoretically guaranteed versus an empirical error rate?
error rate in terms of coherence or something like that?
I'm not sure. I'm guessing when you mentioned that we need 1,000 noisy qubits to correct one, to make one logical qubit. What's the tolerance of that? What are the caveats there?
So the first thing is, I said at least 1,000. It's not clear the number that we will need because it depends on the quantum error correction code that you apply. So what people are trying to do from the theoretical point of view is trying to reduce this number as much as possible. But still, the point is you will need some amount of noisy qubits to correct the state of one qubit. So in the end, you can imagine that like one noisy qubit surrounded by many others that corrects all the time all the imperfections that it has when implementing quantum gates, etc. So in the end, if you want to run a perfect algorithm, which is the requirements for factorization algorithms or Grover search, etc., you need many qubits for each qubit that you want to simulate. And that's the hard part of it. So that's why scalability is also an important thing here. So you need to be able to first construct the chip, like having millions of qubits in a chip. At the same time, this chip shouldn't be enormous. Of course, you need to program everything or construct everything in a small device. You cannot have a room to encode them. And you also need to control all these qubits. So that means cables, that means pulses, etc., and mirrors or whatever technology you use. So that's a very difficult part. And that's why it's one of the reasons why it's not clear which technology will beat the others, because all of them has pros and cons in terms of scalability and also in terms of errors and how many qubits you will need to correct the state of one.
Very good points. And actually, on the subject of hardware, potentially contentious question: do you consider quantum annealers as proper quantum computers?
Yes, because quantum annealers so there are different kinds of quantum computation. So that's a very good point. So I just present the basics. Basically, my talk was focused on digital quantum computation, which means that we have qubits and we have quantum gates that are digital, so similar like a classical computation in these terms. But we also have what is called the adiabatic quantum computation, which is kind of it's related with simulated annealing in classical simulation, which uses the adiabatic theorem and uses what is called the tunnel effect, etc., to also solve problems. The problem with technically adiabatic quantum computation is universal, as it's the digital quantum computation. But for practical purposes, we have what is called quantum annealing, which is not exactly adiabatic quantum computation from my point of view, but it's like a part of it. And the current quantum annealers that we have are not universal, which means that we cannot solve any problem with them. We can only solve what is called optimization problems. And still, even if we can technically solve it, it's not clear if they have an advantage at the moment, because there are, but it's the same issues that happen with digital quantum computation. The qubits are noisy. We are not ever correcting the qubits in the annealer. The coherence is very big, so we need to hold these coherence states, etc. So it's not clear the advantage at the moment, but technically on the paper they should work. Well. So I would say, yeah, it's another way of quantum computing. Maybe it's not universal, but it can be useful to solve many optimization problems. And there are some companies that are trying with that direction. An example is D-Wave. Google has also a project in quantum annealing. We have Kilimanjaro startup, which also works in quantum annealing, and many more, and of course in research centers. So yeah, it's another kind of computation, not super famous maybe, or not as famous as the other one, but technically possible.
Awesome. And now another one that might take up more than the 2 minutes we have left, but let's try anyway. Can you elaborate a bit on how quantum computing addresses the classic NP and P problem?
Okay, so let me move to... So I cannot go into details of how this works in particular, of course.
Yeah, we need a whole nother session.
For reasons. I'm not aware of all the theoretical implications, and I'm not, and I cannot do that now. So the point is, so there are different complexity classes in quantum computing. So We have, for instance, the quantum Merlin-Arthur complexity class, which is, I believe, the kind of equivalent of NP complete problems. And we have the BQP class, which is the quantum equivalent of BPP class. So these problems that can be solved with some probability efficiently with a quantum computer in this case. So the problem here is it's not clear where the quantum algorithms are. So for instance, we know that factorization algorithm is part of BQP problems. But for instance, these variational algorithms, it's not clear in which complexity class they live. What is clear is there are other kinds of problems in quantum simulation, for instance, finding the ground state of some Hamiltonian, etc., some molecule or whatever. Finding the correct ground state is an NP complete problem. So we still know that the quantum computer cannot solve all possible problems. So there are still many problems, or the 3-SAT problem, for instance. The 3-SAT problem is an NP problem, and we don't know that if a quantum computer can solve it or not. The only thing that we hope is that it can find some optimized solution or some local minima solution more efficiently or more quickly than a classical computer. So that's the point. So still, that's why I said in the final slide, I didn't have time to talk with that, but we still need many people to work in the theoretical part of quantum computing and in the complexity classes, because it's not clear which algorithm, where live the quantum algorithms. We only know some of them. So for instance, the factorization algorithm, but that's it. So the that's one of the big issues also in quantum computing. So we need to define these classes properly. But I cannot go into details of what are the differences, etc.
Of course, yeah, we need a whole nother session, I think, for that. So, so sorry to cut you off. This is really exciting, but unfortunately, we're at the end of the time for this session. Now, I have to jump off for the next session, but you're welcome to stay if you want to keep asking questions. I'm sure Alba can maybe spare another 5 minutes. Otherwise, thank you so much, Alba. And that concludes this session.
Thank you, Paul. Okay, so I also have to leave. I have another meeting, but please let me know if you have questions. Just email me or find me in LinkedIn or Twitter or whatever. We'll be happy to answer. Thank you very much for attending.